Well, hi everybody. This is Peter with Fiber Design. Today we're going to be talking a little bit here about PulCalc, the calculator program that I wrote that works in conjunction with some of the modeling, FEA modeling programs, such as RISA, but also others. It'll work with STAD and some of the others. That basically you can take the data from your model. If you want to use, assuming you're using FRP, you've got FRP protruded members in it, and you want to run the capacities of those members. That's what PulCalc does. You should know that you cannot use the AISC steel data in the that would be outputted normally for steel members within, again, I'll say RISA, but it can be others. So we have to do something else. So this is why I developed PulCalc. I developed PulCalc I think 7 years ago, and it's been coming along pretty good. It's we're now into version 3, and version 3 includes all the formulas for the new AISC 74-23 FRP standard that just came out here about, I think, about a month and a half ago. So I've actually been working on V3.0 for about 2 years. Really, ever since the ASCE released the public comments version in 2021. Which they got overloaded in comments, I understand. But really, ever since then, I've been working on this. Once I found out from talking to some committee members that the formulas were not going to change after they received all the comments, and then I went full steam ahead to get this all nailed down. So there's a lot of changes. There's a big, for those of you that have been using PulCalc, well, thank you for those who have been using it. But this is a pretty different program from what was there before. I added a number of I added more profiles to it. I think there's 60 odd profiles in there. As time goes on, we'll add more. There are a lot of calculation tables in PulCalc, because I put outputs in both ASD and LRFD. I essentially had to double all the tables. So all told, now there's something along the lines of 250 internal tables. So there's basically, you can think of it as 250 calculators with results tables for each type of profile, depending upon whether it's LFT or ASD. So, and we also have connections page like we've always had, and a couple other things, and I'll go through it. So why don't we dig into it, huh? See what kind of trouble we can get into. Okay, so hopefully you can see the screen. There's a screen there, and hopefully you can see the cursor. I've had some trouble with this, getting the cursor to show, but I hope you can. But basically, this is the, now we're into the LRFD worksheet. So, and once again, this is based on ASCE 74-23. So the world's first FRP code. I understand Europe is not far behind and is coming right along with it. So, and I've got a couple of things other that I also can discuss here a little bit further down the road here. Okay, so this is the LRFD screen. You basically The highlights in orange is the data that you can put in as a user for your site. Let's say you've got a model going, and maybe it's it can be water cooling tower. It can be a telecom site, such a concealment site, or it could be a platform within a wastewater treatment plant. There's a lot of applications out there. So like I said, the orange highlights is the data that you put in. Where here in line 17, where it says LC1, that's where you would enter, where you would typically enter the load combination that you used. And when you go to the detail page in RISA and you run the model, and assuming it runs all right and all goes well there, you go to the detail page and you can and there's going to be typically a worst case scenario for a load case for maximum stress on bending stress on a member, and also maximum compression compression forces on a member. So this is where you enter the data here. You enter on the starting on the left, which says line 17 LC1. You can enter it in. Oh, by the way, you can enter in. I think it's about 50 different members on there. So we just say for member number 1, you put in load combination 17. So then would say that just say this was M10. So you'd type in M10 there. So I'll do that. Go to hit M10. Let's say it was, what did I say, LC17. I didn't. We haven't got them all up, but LC17. And let's just say that the forces that you picked off the detail page was 555 pounds. So you put that in there now. Now I really should have started and said, now under the green is where these are selection areas. For example, in this case, we've got a 4x3/8 HSS square tube. Now you can choose off various types of square tubes. You can choose wide flange. You can choose all kinds of different members here, channels, including angles and so forth, so on. So we'll talk about angles in a minute. So in this case, we'll leave it as a 4x4x3/8 HSS square tube, and then over on in column G, you can enter in the length. Again, you have a drop down. You can have a drop down box that you can select, and we'll leave it at 10 right there for now. And then what you can see here is we get data here that when as you punch in the data, then the nominal forces that are allowed in for compression, and the nominal compression capacity in terms of in bending capacity, sorry, is also provided. So for example, if we said 555 pounds was what we pulled off the member for compression forces on that member, and then let's say we put in 500 pounds for bending stresses that have been applied to the member, and there we get. So there you go. So we now have for a 10-foot long, we have our allowable, or the allowable would be ASD, but the factored figure of 2,627 pounds is what would be there for. Now, of course, if we change the length, and let's say we reduced it to 5 pounds, to 5 feet, 5 foot length, then you can see that the numbers, that the factored figures for compression and for bending stress, have all increased. Now the maximum compression under line H is now 10,509 pounds, and the allowable, not the allowable, but I still have ASD in my brain. The factored figure for bending stress is now 3128. And then over here on the far right, we have the total. We have the total UC. So, and that's what has to happen. And that again is per ASCE 7423. And that is both of these forces have to be combined to give you the total UC. So now let's take this up to a longer length and see what happens. Let's go up to 12. Let's go up to 12 feet. Well, what do we have here? Look at the total UC now over here on the right. We're now 22% over capacity. So, and notice that it turned that the total UC on the right turned red. So that tells you got to do something different. You've got to rearrange your model. You've got to do whatever you can do to get that number down. Whether it's adding more columns, adding more beams, adding more braces, whatever the case, to get that down. So, and over here, and then these are all in imperial figures. Over on the right here is LRFD. You unfortunately, well, for some anyway, you have to enter in the figures in imperial, but we do output in metric. If for those who want it, I've actually had people from all over the world now buying this, which was a little different than it was before. And we didn't have too many people outside of the U.S., but now we've got people in Saudi Arabia and Israel and so forth, all using PulCalc now. So there you go. So that's that's the story on that. ASD is very similar. Just like before, you can enter in the site information up here on the left, and you basically put in the same data over here on the right. The load combination you use, the member name, and then you can actually enter in the resultant figures out of your model. And then you can get the capacity of each member. So now there's some other things too here. We also have time effect factor in here. This was in PulCalc, the earlier PulCalcs. Time effect factor would be a consistent load. For example, a snow load on a roof. So something along those lines. So that's something that you have. That again, that's a drop-down box. These values here are values again that are in ASCE 7423. I think that's in chapter 2. So so there you go. It's all pretty straightforward. And basically, and also the compression forces under compression. You can see here under the yellow line here, which is line 10, we actually tell you what chapter these formulas come from. For example, in the time effect, it's table 2. It's in table 2.3-1, and so you can see. So we did that really as a means, so we can really help you out with all that. It makes it a little easier to find all this information. So, but for the most part, the compression forces are chapter 4, and the bending forces are chapter 5. So, and connections are chapter 8. Okay, so let's go over to model properties. Now, this is pretty much the same that existed in PulCalc before. This is the information you enter into your model. The modulus of elasticity, the shear modulus, Poisson's ratio, density, so forth, so on. All of that was the same as PulCalc before. If you didn't use PulCalc, you just make sure you just enter it in. You enter all this information when you create an FRP properties within your model. So not FRP materials, under materials in your model. Now, what is new to PulCalc also, and this was a lot of work, was here you can actually enter in the coupon properties for a particular manufacturer. Now, what I have listed here are what I call generic properties. And also, by the way, again, this is all highlighted off by the values the user puts in, values that are within the program, and information, and so forth, so on. Information's in yellow, and the orange is data you put in. So it's important to realize that this data, if you change this data, it's going to change all of the results in your capacities for your members. So you do have to realize that. But what you can do with this is you can set, let's say you wanted to use a specific manufacturer, such as Creative Pultrusions. You can put all their data in here, and it'll give you the same data information that would match their products. So now the other thing too is that you have to use you also want to make sure you try to use the same section properties. I use again, these are common section properties. Pretty much all the major pultrusion manufacturers in the U.S. pretty much use the same section properties. If they're not, they're extremely close. So now, and also in your model, in regards to section properties, you don't have to. Well, I'll say it this way: if you're going to use, how am I going to explain that to you? Okay, so the most common, the easiest means that I have found to use to create profiles, to use a particular profile of an FRP member within RISA, and I'm sure stats would be the same, is I like to use hot rolled. Now, and now there's a lot of common steel shapes that are nearly identical to the FRP shapes. This would be the case of box shapes, angles, some of the channels. But if it's not the same, you've got two choices. One, you actually have more than two choices, but the typical choices would be you could modify one of the ASCE shapes and then change the section properties, and then save it as an FRP profile, or you can create an FRP profile from scratch. Now, some of the profiles, like for example, some of the channels and some of the I-beams and wide flange beams can be quite different. So just be careful of that. So and it's really easy to do. So we've listed, by different types: I shapes, W shapes, box shapes, so forth, all through here. So that's a story on program properties. So just be aware of that. And now I do list, if you do go off into a tangent, I do list both. You do go off and change anything. I do list common default properties that I recommend as default properties. That would put you at common shapes and profiles that are used throughout the pultrusion by most of the pultrusion manufacturers. So in fact, these values tend to be really the most basic. It would be polyiso resin based versus vinyl ester and so forth. So on vinyl ester protrusion tends to have higher, stronger properties and so forth, so on. So, okay, so moving on to connections. Just as with PulCalc 2 and earlier, we've got connection properties here. Now, there's quite a bit more to this than there was in the earlier versions. Again, just as we had before, it's bolted properties. Once again, we try to automate it as much of this as we can for you. It's for a lot of this is for, and again, most of these connections are really right out of 7423. So. So these are for common bolt types, A307s, stainless 316, so all various types of bolts, metric 4.6 ISO grades. What you won't see on here is A325s. We do not recommend using A325 bolts on FRP materials. For the most part, if you load an A325 bolt to its maximum capacity, you probably will exceed the pin capacity or the bearing capacity of the fiberglass material or the composite material that you're connected to. So that's why that's the case there. Down below here, we've got a lot of this is right out of 7423. Cope flange connections. If you're going to use a cope flange connections, and that's a frequent thing. That's a real common practice. We can calculate what the connection capacity of the coped member. So cope connections is there now. It really, I never remember if I had it there before or I didn't. I may not have. And then this again, a lot of this comes right out of 7423 for bolted connections. Now, keep in mind now, these are all steel bolts. 7423 has accepted, as in not there. FRP bolts. They decided to not address them. I wish they did, because becoming more and more popular. They're obviously heavily used in the telecom world. They're used in the world where corrosion is a big deal, hypochlorites and that sort of thing. But they're also becoming more and more popular because of corrosion factors and all that. But they're very weak. So you won't find them here in LRFD connections, but the AST page is there. So if you're still using AST, we could run some FRP bolt connections there, but you got to be careful there because, and this is a big deal, the committee in all their greatness decided to only allow metal connections to steel bolts and steel clip angles. Nothing else is allowed. However, what we can do is what they do allow is that one can have a connection tested per section 2. I think it's 231. And so that's good news. And as a matter of fact, I am leading a group, a working committee group, and trying to get funding to get testing done on a lot of common FRP connections. So we started on this a few months ago, and it continues on. I've applied for some grants. We're going to work. We hopefully are going to work with a couple of labs up here in the Northeast and get the ball rolling here. The only clip angles that I know that have been out there and out in the public are the by CPI, Creative Protrusions Group, well, CPG now. They do have some connections. These connections are quite limited, though, so you have to really look at what the connections were all about. So you have to make sure you follow the way they show it on here. For example, these connections are really for I and W shapes, and they're really not for anything else. So that's so anyway. So we got a long ways to go here in terms of connections. So, but there is a little bit of time, at least as far as connections. So, now again, ASD connections are pretty much the same, very similar, just the formulas are slightly different. Just because the load combinations, that's one of the factors. The load combinations are different. Again, that's in 70, well, not the ASD. ASD, I don't think ASD load combinations are in 7423. But it's, for those who are familiar with it, it's not that big of a deal. And then, if I haven't put you to sleep yet, the plate connections also is here on in the plate connections worksheet. And what it is I actually ran. I have my own FEA program, and I actually ran numbers for different types of laminates down here between lines 20 and 24. We've got I've got common plates, and these would be typical plates that I use throughout the construction industry. I've got a hand layup molded plate. You can choose the thickness. You can choose the laminate length, the laminate width. Now, what it is, if you decide you want, what you can do is you can choose the laminate from the drop-down menu. So if we go to laminate 3, so that's protruded laminate, and that's lengthwise. So we got to remember now, in the protrusion world, they typically have the lengthwise and the crosswise strength factors are very different because they tend to have they tend to have the strength materials, the fabrics that provide most of the strength running in mostly in one direction. So if that means something for you, then you want to pay attention to that. And then I put an other down here too. So what you can do is you can calculate based on your load, such as wind. You can calculate what size panel you need, and most importantly, this will tell you what you need for framing distances. So in this case, if it's a width, then that means we would need on the line 6 we would need a 36 inch width here. So that means you would run your columns at 3 feet on center. So anyway, so that's a story. That's a quick run through here on PulCalc. I hope this helps. And if you like it, throw a few comments down. If you have any questions, send me an email. You can get through the web. We've got contact information in the program here, and www.fiberdesign.com. You can go through there, or also peter@fiberdesign.com. That's FIBR design.com. So any comments, shoot me a message, whatever you like. And even if you'd like if you like this little tutorial, then please do that. So that is the story. I hope it's been helpful, and look forward to talking to everybody about PulCalc V3.0. It's been off to a good start.